All right, so in this lab, we're going to study some acids, bases, and buffers. And the first thing we're going to do is we're going to try to find the pH of an unknown. And so we're going to do this using indicators. And an indicator is simply something that changes colors depending on pH. At least the indicators we're using. You can use indicators for other stuff, but we're talking about pH here. Right, so we've got some kind of unknown and we want to find its pH using indicators. So here's how we're going to do this. You can look in your lab manual and you'll see a table of indicators. So you've got the indicator name on the far left and then the pH and the colors on the right. So for example, this methyl violet one, right, you can see here it says yellow. This yellow corresponds to a pH of -1 or less, right? So if you have a pH of -1 or less, your solution will be yellow. And then on the other side, it can turn to violet. So I think that's purple. And so it'll turn purple if your pH is greater than or equal to 1.7. And so, right, if it's yellow, you know it's somewhere around this range. If it's purple, you know it's somewhere around this range. And then if it's somewhere in the middle, you're going to get a color somewhere in the middle. So if you take kind of yellow and purple, I guess you get brown. I'm not a color expert. So you get brown or something like it. So the pH, if you get a brown, that means that your pH is equal to somewhere between -1 and 1.7, right? So you can see how these indicators can be useful. And you need to use multiple indicators because you don't know where your unknown's going to be. You don't know exactly. And so depending on these color changes, you can get a rough estimate of the pH. And so we want to get a little bit closer. To get closer, we're going to do some more experiments. And so maybe you found out that your pH is somewhere between this -1.0 to 1.7, right? Because you saw this brown color. Right, so you know it's somewhere around there. And so what you would do is you would find some solutions that bracket it. And so you'd use known solutions, known pHs, right? So maybe you would use a known pH of -1.0 and then maybe a known pH of maybe 1 or 2, something like that. Let's go with kind of 2. And so on this end, you'll get more of a yellow color. On this end, you'll get a more of an orange color, or, whoops, my bad, purple color. And then you could get a known solution of a pH maybe of 1 and 0. And these both would be somewhere brown, right? Whereas the one on the right would be more purplish brown, and the one on the left would be more kind of yellow brown. And so on the basis of comparison, you could take a look at this color and see which color looks more like, right? The one that it looks more like, it's closer to that pH. So if it looks more like this yellow brown, it's going to be closer to a pH of 1. If it looks more, oops, I mixed these up, didn't I? 0 should be on this end, 1 of this should be on this end. If it looks more like this purple brown, then the pH is probably closer to 1, right? And so you'll see I do this in the video. You can't see it very well in the video, and I freelanced a bit. I didn't follow the manual exactly, which it didn't end up being the greatest idea, but it still works decently well. But you can't really see well in the video. But the initial step using the indicator, that works well. It's just the second step where we're kind of trying to bracket in between things. You could see it better in person. And so that's kind of the old school way to do it, right? Use these indicators, that kind of stuff. Nowadays, we pretty much just use technology. So you can use a pH probe here. And so a pH probe is simply an instrument that reads pH. And so you just buy this instrument, you stick it into your solution, and it'll read the pH for you. And so we'll do that as well to compare with our indicators and our pH probe, see if we get similar results, which we should. All right, so for this part of the lab, what we're going to try to do is have an unknown. So we've chosen unknown B, for example, and we're going to try to determine the pH of it. First, we're going to try to use it, try to determine it using indicators. And so you can see I've put some of my unknown in these 7 well plates. And then we're going to add these different indicators to tell us about this. So the way this works is an individual indicator changes colors depending on the pH. So for example, methyl violet goes from yellow to violet. If the pH is less than or about -1, it's going to be yellow. If it's 1.7 or greater, it's going to be violet. If it's in between, it's going to be in between yellow and violet. So by judging the color, we can determine our pH. So let's go ahead and get started. Let's add some methyl violet and think about what that tells us. So I'm just going to get some on the end of the toothpick, mix it into here to my solution. And you can see that it stayed this violet color. So our pH is greater than 1.7. Next up, we have malachite green. I don't know if I'm saying that correctly. So this will be yellow or green depending on the pH. Right, definitely looks more green to me. So that tells us that we have a pH greater than 1.8. Next up, we have thymol blue. And that'll be red or yellow. Just grab a little bit more. And so you can see that's giving us a yellow color, indicating that we have a pH greater than 2.8. So normally we'd use this M. Crescel purple, but we actually ran out of that. So we're going to use methyl orange instead, and that's going to go from 3.0 to 4.4, and this red to yellow orange exchange. And so you can see it's kind of yellow-orange. It's definitely not red, so probably higher than 4.4. Next up is bromophenol blue. And you can see it gives us a blue color, so probably higher than 4.7. Next up, we have this alizarin red. We'll go with that. So as you see, it can be yellow to red if it's between 4.6 and 6.8, or it can be red to purple if it's between 11 and 12.4. And so we can see that this color is yellow. And so you can see all these other previous data points told us that our value is greater than, let's see, probably about 4.4. And then this alizarin red, with it turning yellow, it tells us that it's somewhere between 4.6 to 6.8 and being closer to 4.6 than 6.8 because we've definitely got more yellow than red. So we're kind of probably narrowing it down a bit. Next up, we'll try some litmus paper. And so litmus will change colors depending on whether the solution is acidic or basic. So if it's more basic, higher than 7 pH, this blue will change colors. That's my bad. My bad, I messed that up. So if it's blue and changes it to red, that means that it's acidic. So it's closer to this 4.7 than the 6.8. And we can try it with the other color as well. We can try with red litmus paper. If this red litmus paper were to turn into blue, that would tell us that we're more acidic, right? That we're closer to the 6.8 or higher. And so you can see this one is indeed not changing colors, while the blue litmus paper did change colors. Right, so we're closer to this red side, which means that we're closer to this 4.7. And so we could probably guesstimate our pH is probably somewhere between like 4.5 and let's see, this is 6.8 right here. This is 6.8 right here. So somewhere between maybe like 6. We'll narrow it down quite a bit. All right, so we've narrowed our pH down to somewhere between 4.5 and 6. And we said maybe this alizarin red would be a good indicator because it's right between there, right? 4.5 to 6.8. We know our pH is somewhere around there. We don't have any other good choices that kind of get 4, 5, and 6 other than litmus. So we can test these two and litmus, and then maybe we could use bromophenol to say it's higher than 4.7, right? So it did turn blue, so it's probably closer to 5. So let's compare these on the basis of comparison and check out their color. So what I have here are known solutions of pH 4, 5, and 6, and then our unknown. And so I'm going to put alizarin red in each one of these, and we'll see if we can see which one of our unknown looks most like our knowns, and from there we can figure out the pH. See, our pH 4 is quite yellow. Our pH 5, a darker yellow, maybe some would even say an orange. So we can see the different colors there. Let's check out our unknown, see which one it looks the most like. And so you can see we've got all these different colors. If you look at our unknown, I would say it looks most like pH of 5, right? The pH of 4 and 6 both look a little bit more different. Unfortunately, the camera is not quite catching 6 in its best color. So just slight technical issue there. But you can tell the 5 and the unknown look the most similar, and the 4 and the 6 looks less similar than the 5. So our pH range is probably somewhere around 5. All right, so we showed you the old school way to find pH using indicators. Now we'll show you the kind of new school way using instrumentation, right? This is a pH meter. So this is just a generic kind of reads different stuff. And then it's attached to this pH probe. So you take this thing out of here. And you stick it into your solution. And in theory, it tells you the correct pH. But before we can do that, we have to calibrate the instrument. The instrument can read these numbers, but it doesn't know what is what. So you have to tell it, this is pH 2, this is pH 10, whatever, and then it'll learn it, right? And then you can do whatever you want, right? So I turned it on using this on button right here. I'll flip it over to the back, pull out the stylus, which is right here. And then I'll simply just click on somewhere. Sensors. And then I will press this calibrate button. Now yes, this electrode amplifier. And then I will click calibrate now. You can see I have pH selected down here. And so what I want to do is take one of these well plates and then put a known buffer solution in it. So first I'm going to use buffer solution 2. And so I know this is pH of 2, and so I'm going to put that in there. It's going to read a voltage, and then I'm going to tell it whenever you read this voltage, that means 2. So put some in this well plate. You just need to cover the bottom disc of the electrode. So you don't need much. We'll take the electrode out of here. And you can see on the bottom there's this kind of flat black disc. It's actually glass. And so that's what does the actual reading. That's the only part that needs to be covered. Before you do that, you want to rinse it off with some distilled water. Probably further away from the electronics, but I'm going to do a little bit close just so you can see me doing it. All right, just shoot some distilled water at it, clean it off. And then just take a little towel, wipe it down. Don't scratch the bottom electrode though, so just wipe kind of the sides. And then place it in your pH 2 buffer. And you can see the voltage is changing. And so we want to give it a minute until it stabilizes. And you can see now it's hanging out at this 1.8. And so this is a pH of 2, so we want to tell it this is a pH of 2. And then you press keep. And now we're going to do a different value. So for this one, we're going to do pH of 8. So we know this is pH 8. Pour it into this second well, or this third well plate. Rinse off our electrode with distilled water. Plug it into the pH 8. See our voltage is changing. Wait for it to stabilize. And then we tell it this is a pH of 8. And then we press keep. And then you simply press OK. And now we're going to do our unknown B, right? So we've got our unknown B here. Put a little bit of it in this fifth well, and we'll see what the instrument tells us the pH is, right? Remember, we guessed around a pH of 5 from our indicators. So wash it off. Put it in our unknown. And then wait for it to stabilize. And so you can tell it's giving us a pH of 5.12, which agrees well with what we found out from our indicators. And so it's just another way to do it, right? Old school way, new school way, both have advantages and disadvantages, right? You think the technology is better, but really the disadvantages are cost. And technology is great when it works, but we all know it has a way of not working right when you need it. All right, so move on to the next step. So in the second part of this lab, we're going to take a look at some pH of some salts. And so remember, salts are made out of positively charged cations and negatively charged anions. And so you can have a bunch of different salts, something like, sodium chloride, ammonium chloride, or sodium phosphate, right? And so the question that you want to know, is this acidic or is it basic, right? What could you do to figure this out? Well, you could simply make a solution, and then you could check the pH using your pH probes or indicators. In this case, we'll use the pH probe, right? Acids will make the solution acidic and thus less than a pH of 7, and bases will make the solution basic and thus have a pH of greater than 7. And so they'll change it pretty significantly. You'll see the probe's not completely accurate. And so if it's approximately 7, you can pretty much call that neutral. All right, next up, we're going to use our handy dandy pH meter to test the pH of some salts. So we'll start off with some sodium chloride, and I've already got the pH meter in the sodium chloride, so we can see it's reading about 7. Rinse it off. Next up, we'll go with potassium bromide. And so we can see that this is also reading approximately 7. There will be some drift in the instrument. Next up, we have sodium nitrate. And so again, we can see a pH of about 7. Next up, we have some sodium acetate. And here we can see a pH of above 7, almost 8. Next up, we have ammonium chloride. And we can see it's a pH below 7. Remember, this is just qualitative, so we're just trying to see if these salts are acidic or basic. Next up, we have potassium carbonate. And we can see a pH well above 7. Next up, we have ammonium sulfate. And so we can see here that we have a pH slightly below 7. Next up, we have copper 2 sulfate. And again, a pH well below 7. And then last but not least, we have iron 3 chloride. And you can see we have a pH of well below 7. So compare that to what you think should happen and see if you understand the concepts or not. All right, so in this next part of the lab, we're given an unknown solid, an unknown weak acid, and we want to know its pKa. So remember that pKa is equal to the negative log of the Ka. And remember that the Ka is the acid dissociation constant, so it's equal to the products, which is the H plus and A minus, over the reactants of HA. And so remember that the more H plus you have, the higher the Ka is going to be. And then the lower the pKa is going to be, right? So lower pKa means stronger acid. And so think about how we're going to figure this out. Remember, we can read the pH of solutions, but the pH of solutions is dependent on the pKa of the acid and the concentration. And in this case, since it's an unknown, we don't know the molar mass. Right? We don't know the molar mass. And so if we don't know the molar mass, we can't know the concentration. And if we can't know the concentration, we can't find our Ka, right? Because we don't know the concentration of these components. And so how the heck are we going to solve this? So we're going to use something what's known as the Henderson-Hasselbalch equation. And so this equation tells us that the pH of a solution is equal to the pKa of a salt plus the log of the conjugate base over the weak acid concentrations, right? And so think about these variables, which ones we can solve for. pH, we can find that from our probe. But that's not enough, right? We still have a number of variables here that we don't know. We don't know the pKa, we don't know the concentration of A minus, and we don't know the concentration of HA. So we still have more than one unknown. And so how are we going to solve this? So we're going to do a little trick. And our trick first starts off with separating equal amounts of HA into 2 containers. Right, so we're going to have equal amounts of HA in 2 containers. In our first container, we're just going to leave it alone. We're not really going to do anything to it. In our second container of HA, we're going to add base to it. And we're going to titrate this until it's basic, right? So we're going to add some sodium hydroxide to this. And then we'll convert pretty much all of our weak acid into its conjugate base, right? So we're pretty much going to have all conjugate base in solution 2 and pretty much all HA in solution 1, right? It's not exactly all, because if you think about the equilibria, but it works out in the end. And so after that, what we're going to do is we're going to mix these two solutions, right? And so when we mix these two solutions, we're going to have equal concentrations of HA and A minus, right? They're going to be equal to one another. And so how the heck does this help us out? Let's go back to the Henderson-Hasselbalch equation and think about it a little bit more. So it's pH is equal to the pKa plus the log, I think it's actually minus, the log of A minus over HA. And now we know these two are equal to one another, right? And if they're equal to another, any number divided by itself is equal to 1, right? If they're both 0.1 molar, 0.1 molar over 0.1 molar is equal to 1. And so if you type in your calculator the log of 1, you'll find that it's equal to 0. And so all of this will thus go to 0. And thus our pH is equal to our pKa. And so if we use our probe to find the pH, we've also found the pKa of our unknown. And so I think that's a pretty clever trick to find out the pKa of an unknown. All right, so for this portion of the lab, we have an unknown solid, and we want to find its pKa. So I've gone ahead and done some of the steps already. I've taken some of my salt, dissolved it in some water. You can still see there's still some solid left. I've decanted 50 mils into each one of these Erlenmeyers. So decanting just means pouring while leaving the solids behind. So I've taken 50 mils of each. To one of these 50 milliliters, I'm going to just put it away on the side for now. And then to the other one, I'm going to add 2 to 3 drops of phenolphthalein. This will be our indicator. So there's 3 drops there. And we know it's an acid because it hasn't changed color yet, so that means acidic. When it turns basic, it'll turn pink. And so what we want to do now is basically make the salt of this acid. And to do that, we're going to titrate it with 0.2 molar sodium hydroxide. Now in this experiment, we're not qualitatively determining how much sodium hydroxide we added, so there's actually no need to use a burette. So I'm going to cheat a little bit. I'm just going to pipette in my sodium hydroxide. So pour it into my secondary container because you never want to take from your primary container. That'll be more than enough. Lower this a bit. And now I will just roughly titrate. So I'm going to add my base to my acid until a pink color stays for about 30 seconds. We get a pink piece of paper real quick. A white piece of paper.
If you look really closely, there is indeed pink being formed. It just goes away super quick. See that pink there? So we're just far from the end point, that's all. Just keep chugging along. Got a pink color there. Cool. And it's staying for about 30 seconds or a little bit over 30 seconds. And so what we'll do now is take our other solution that we did not titrate it, and then we'll mix these two, right? This acid has been fully deprotonated, while this one has not. So when we mix these two together, we will have equal amounts of the acid-base conjugate salts. Mix that in there. And now when we take the pH of this from the data we receive from that, we should be able to calculate the pKa of our unknown. All right, back to our pH probe. So I already tested, made sure it's still calibrated, and so now we can stick it into our solution to find the pH, and from that infer the pKa. Put that in there. Give it a little bit to calibrate, or not calibrate, but equilibrate. And we can see we're getting a reading of about 5.2, something like that. And that'll be the pH of our solution, and from that we can find the pKa.
All right, so for our final set of experiments, we're going to take a look at some buffers. So remember that buffers are mixtures of weak acid-base conjugate pairs. And so let's take a look at two solutions. In this upper solution, we're just going to have water, so all we've got is H2O molecules floating about. And then in this bottom solution, we're going to have a buffered solution. So we're going to have weak acid-base conjugate pairs. In this case, I'm just going to write ammonia, NH3, and ammonium, NH4+, right? Those are acid-base conjugate pairs. And so let's take a look at what happens when we add acid to both of these solutions. So if we add acid to the top solution, it's going to interact with the water and form this H3O+. And so remember that pH is equal to the negative log of this H3O+. And so if our H3O+ changes, our pH changes. And so as soon as we add some acid, we're going to have a change in pH. Now, when we add the acid to this solution, instead of interacting with water, it's actually going to interact with our weak base. Our weak base is going to absorb that H+ to form some NH4+. And then, of course, we'll have that other NH4+ still in solution. And so you can see here that the concentration of pH, or the concentration of H+ is the same as it was before. This H+ did not interact with water. It actually got absorbed. It got buffered by the NH4 or the NH3 to form NH4+. And so if our H+ stayed the same, our pH stays the same. And so you can see how buffers prevent drastic changes in pH. And same thing if you add base. So for example, if you add base, you'd deprotonate one of these waters and you'd form a hydroxide, right, and some water. And then remember that the concentration of H plus times the concentration of hydroxide is equal to a constant, 1.0 times 10 to the. And so if you change the concentration of hydroxide, you're also going to change the concentration of H plus and thus your pH. And so if you add some base to just water, the pH can change drastically. On this other hand, what happens when we add some hydroxide here? Now, instead of that hydroxide taking a proton from water, it can take the proton from our weak acid, right? Our NH4 plus. And so what we'll be left with here is 2 NH3s. And so again, here our concentration of hydroxide stayed the same because our buffer buffered it, right? And if our concentration hydroxide stayed the same, that means the concentration of H plus stayed the same. And if the concentration of H plus stayed the same, the pH stays the same. So you can see how a buffer solution protects from large changes in pH. Now, naturally, this isn't an unlimited ability. If you add enough acid, you will change the pH drastically. So let's check out how this looks like in real life.
All right, so last but not least, we're going to check out our buffering ability, see what buffers do, right? They buffer the pH change. So we have our buffer made from our weak acid base complex, split up into two 25 mL containers. We have some buffer standard solution split up into two 25 mL containers. And then finally, we just have some regular deionized water split up into two containers. And so to each one of these two containers, one of them we're going to add acid, one of them we're going to add base, and we're going to see how the pH changes. So first, let's take the pH of our salt solution that we made. And so you can see it's still hanging around right about 5.2. And so to this, we're going to add 5 drops of sodium hydroxide, right? A strong base. Let's see what happens to the pH when we do so. So 1, 2, 3, 4, 5. Give it a little stir. And you can see we don't really have any change whatsoever. Let's try to see what happens when we add acid to it. Wash off our probe. Put it in our solution. Again, kind of hang around 5.2. Add 5 drops of acid. 1, 2, 3, 4, 5. And so in this case, our acid is 0.1 molar hydrochloric acid. And so again, we can see that the pH has not changed significantly. All right, a little bit down, but not really too much change. Let's skip over our buffer solution, standard buffer solution, and let's go check out the water next. So stick this probe in this pure water. You can see it's reading slightly acidic. Some of that is drift. Some of that is the fact that there's carbon dioxide in the air that can go into the water, form carbonic acid, and slightly acidify the water. So let's add our 5 drops of sodium hydroxide and see what happens. Give it a little stir. And you can see our pH has skyrocketed up, right? This is not a buffered solution, so that's exactly what we would expect. Let's check out the same thing, but now by adding acids. And so it'll continue to drop for a little while, but you can see the trend there. Let's see what happens when we add some acid. You can see it's going down very slowly. 1, 2, 3, 4, 5. Give it a little stir. And look at that. Our pH has dropped rapidly, right? Again, this is an unbuffered solution. You add acid or base, you make the solution acidic or basic almost instantly, right? Very small amount. We've got 25 mils of water and only 4 or 5 drops of not very concentrated acid and base, right? It's only 0.1 molar. So again, let's check it out with our buffer solution. So again, this is buffered. It's a pH of 10. It's a standard solution. So we can also check out how much our instrument has drifted. And you can see there certainly is some drift there, but it's not too terrible. It should be reading exactly 10. These things go through a lot of student abuse, and so they're not the best things ever, but still pretty decent. Let's add our 5 drops of base. 2, 3, 4, 5. Give a little stir. And we can see that there's no change. Again, it's a buffered solution. Finally, let's just check it out by adding some acid. So again, we're in our buffered solution. We're reading about 10. Add some hydrochloric acid. 1, 2, 3, 4, 5. Give it a little stir. And again, we see no real change in the pH. So you can see the function of buffered solutions that don't change pH and pure distilled water over here to my right that changes pH very rapidly upon the addition of just a few drops of not extremely concentrated acid and base. Cool.